Did you know you were born a math genius? In fact, there was a researcher named George Land who was hired by NASA to come up with a predictive test to find the most creative minds that could help around the time of the Apollo missions with what they were working on there. And what he found was that 98% of 4 to 5-year-olds in the Head Start program scored at the genius level on the same test he'd been hired by NASA to develop to screen for their best talent. And this test was very predictive. But what he found was as he gave this test to the same students over the course of 5, 10, 15 years, all the way up to age 31, there was a complete figure ground reversal. And only 2% of adults, 31 and older, could do what they could have done at 4 and 5 years old. Why? Well, he found that it was that voice in our head that thinks, no, that idea is stupid. They would make fun of me for that. Or no, that would never work. We never allow ourselves the chance to explore different ideas and play with things before we start to entertain the fear of being criticized, called stupid, or failing. And today, what I would like to do is show you 3 things you can do to get your math genius back. You were born a math genius. You were born with the ability and potential, like Glenn Doman said, every child at the moment of birth has greater potential intelligence than Leonardo da Vinci ever used. He found that through his experiments. I have found that to be the case in the students that I've helped. And today I'd like to give you these 3 tools you can walk away from this video from to explore life a little different, to open up some doors and possibilities for you. So the first thing I want you to understand, excuse me, I had to clear my throat. The first thing I want you to understand is that no one is anything all the time. I got this way of saying this from Dr. Ellen Langer, the mother of mindfulness. And the reason it's so important is because this is what happens in class. You're in class, you're a kid, you're afraid of looking stupid in front of your friends, in front of your enemies, in front of your frenemies, in front of the teacher. And when a math problem is presented, there's that ticking time clock in the back of your head and it says, oh my gosh, oh my gosh, oh my gosh, what's the answer? Because you've all been put in this race none of you asked to be in. And what's implied in that environment is that the first person to raise their hand and get it right, well, they're smart and they are good at math. And everyone coming in second place is the first loser, right? Wrong. That's such crap. I had a wonderful conversation with a chemist a few years ago, a very accomplished chemist, who said, you know, these math Olympiad programs are great, but they give other students, the ones who are not interested in competing, the wrong idea, because math and deep scientific understanding, the kind that leads to great contributions, has nothing to do with racing a clock. It has to do with deep thinking and understanding and creativity, which is a process that needs percolation. You need to sleep on things. You need to consider them over time. You need to be brushing your teeth and suddenly the answer comes to you out of nowhere because you've been obsessing over it forever. It has nothing to do with getting the answer in 30 seconds. And so if no one is anything all the time, we confuse the stability of our mindset, the stability of our ideas, with the stability of the world. The world is constantly in flux, always changing. The things we think we know, we really don't know them as well as we think we do. And you can discover that anytime you take a second look. And this is the most important thing I want you to understand. You are not bad at math. What you may have, you may legitimately have, are memories of the unsavory experience of feeling like you're being judged by people as stupid, as less than, as incompetent, and that is very real, and it's a feeling I want to free you from. So just understand, no one is anything all the time. We all have moments where we could be looked as good or we could be looked as bad at math. And if you have that understanding, it can start to open the door to mindfully exploring, well, maybe the problem is not that you are this thing called bad at math, whatever that means, but that maybe if you had a different way of thinking, you could become more efficient. Which brings me to number 2. So here's number 2. You want to use patterns that make sense to your brain. What do I mean by that? Well, in the West, for whatever reason, we read left to right, we write left to right, but we teach our children these terribly inefficient algorithms, which are all unrelated. Right? Math feels like this endless encyclopedia of disconnected, disjointed techniques that were just kind of mashed together at the last second. And that, I will suggest, is a very poor way to learn. Why don't we use the patterns that make sense to our brain, the patterns we use already? Things like looking for proportion, looking for missing pieces, doubling and cutting in half. And I'm going to give you an example right now that will allow you to do something if you haven't seen any of my other videos in base multiplication, you didn't think you could do before. And hopefully when you have this new skill, you'll think to yourself, if I could get that new skill in just a few seconds, I wonder what would happen if I spent a few weeks or months at this. Because if you spend a few weeks or months learning these patterns that I teach on this channel, it really will unlock the world of mathematics for you. So we want to use patterns that make sense to your brain, and I'll show you a few of them right now. So suppose I had a problem like 99 times 98. Could you do that mentally in just a few seconds without a calculator or scratch paper? If I gave you 5 seconds, which doesn't sound like a lot, but that's this. More than enough time. Way more than enough time given this method I'm about to show you. So let's relate both of these, 99 and 98, to a base of 100. And I will explain why this works in a moment. But just for now, I want you to see this pattern and how quickly it will change what's possible for you. So this 99, we're going to look at this 100 and say, how many away is this from 100? Well, it's 1 away from 100. Or we could say a deficiency of -1. Now you see I wrote 0, 1 instead of just 1 because in my base I have 2 zeros, and that'll become important in a moment. But now let's look at 98. This is -2 from 100. Okay? So what I do now, if I want to multiply these, I take this pattern here, a crosswise subtraction, either 1 from 98 or 2 from 97. And you'll notice as you do that, two things. One is very, very quick, very efficient. It can happen in half a second. You could just see whichever one looks easier to you. To me, taking 1 off of 98 looks easier for 97 with no mental struggle. Now, to find the right-hand side of my answer, I simply multiply these two together. -1 times -2 is +2. So in just a few seconds, once you understand this pattern, finding the deficiencies and working crosswise, you can multiply 98 times 99 in your head mentally in just a few seconds. We'll try one more so you get the hang of this pattern. Here with this example, 96 times 95. In the last example, I wrote everything down. I think that's a mistake I've made in teaching this, is I'm writing down everything I'm thinking, which does help everyone understand what I am saying so they're not confused by the mental math. But this system is a system of mental math. It's meant to give you the mental agility to easily handle quantities so that you don't make those mistakes and you're not intimidated by problems that seem like they're out of your range. Because once you develop skill with these patterns and this mental agility, it's the same exact patterns you're going to use even on higher algebra and calculus. So the skills you're building here are exactly the skills you're going to use to make higher math easy. Easy to comprehend, easy to think creatively with, easy to calculate. So for this one, I'm not going to write those. We're just going to take the last example, and now I'm going to show you how easy this is to do mentally. So remember, my base is 100. These are both near 100. And when I see 96, because 6 is a complement of 4 to make 10, right? This is 4 away from 100. As soon as I see this 96, I think -4. Not too difficult, right? Not too complicated. As soon as I see 95, I'm thinking -5. Now I could take this -5 from the 96 or this -4 from the 95. You can see either way, I'll end up with 91. And then if I have 4 times 5, it's 20. Now, without going into the geometric proof for why this works, I've showed that in other videos, but for this video, I would like to simply suggest to you that now that you've seen how this pattern works, even if you don't feel like you could go off and do it yet, I want to show you another pattern that is even more simple than this, that will help you with arithmetic, multiplying 2, 3, 4, 5-digit numbers. It will help you with division, any length of division. And you can take that pattern and march right over to algebra with it and do equally impressive things. All right, now this problem is called, this pattern is called vertically and crosswise. And so this is what the pattern looks like. We'll start with 2 digits, because that will make it clear, and then we'll go to 3 or 4 digits. So you can see here, I've made a model of the 3 steps we're going to take. We're going to multiply vertically on the left. then we're going to multiply crosswise, and then we're going to multiply vertically on the right. Now, why do I do this? What I'm training my brain to do is start with the highest order of magnitude and count each column in precise order from left to right, the way I'm already used to thinking. At least in the West, right? We read and write left to right, so this makes total sense. But there's another mathematical reason this is so great when you get to algebra, is when you're dealing with higher order polynomials, the ability to see what the most significant figures are first, and the ability to multiply them or divide them in order from left to right, especially when you're squaring or you're trying to find roots, becomes essential. So here we would have 2 3s or 6. Then I would have 2 1s or 2, so 2 times 1 is 2. 3 3s are 9, and I add the 2 and the 9 mentally for 11. And you see, so I carry this 1 because I had 11 here. That's 11 tens. That's why we carry the 1. It's going into the hundreds. And then here on the right, I apologize, I ran out of recording time. So I have 2 3s or 6, and then I have 2 1s. So 2 counted one time is 2, and I add that to 3 counted 3 times. So 2 and 9 becomes 11. And you can see that's 11 tens, so I carried this 1 into the hundreds. And then finally on the right, I have 3 times 1 is 3. Now I can see this is 713. And so the reason this is so important is because what I'm training my brain to do is I'm training my brain to start with the highest order of magnitude and systematically work left to right. Now this not only helps me multiply efficiently, like you can see here, I can reverse this process, and division now becomes not some strange process unrelated to my algorithm for multiplication. It becomes simply the reverse of it. So if my brain can do this in one direction, now all I have to do is go back the other direction to handle any kind of division, even algebraic division. And now we're going to go into example of algebra, because where this really shines is in algebra. When you're finding higher order polynomial equations, when you're finding roots, when you use a modification of this called the duplex, the triplex, and so on, it allows you to do things most people wouldn't dream they could do without a calculator, even if you used to think you were bad at math, which I hope you understand isn't even possible. And actually, before we move on to the algebra, I want to show you something that happens when we multiply that is obvious if you look for it, but most people have never been taught to look for it. So when I'm multiplying 21 by 34, if I split the number into these two pieces, I say 20 plus 1 and 30 plus 4, something will become very obvious to you. And I want you to see this. When I multiply 21 30 times and then 4 times, the results, the products of this multiplication are going to be in ratio 3 to 4. Here's what I mean. 20 times 30, 20 30s is 600. Now watch, I multiplied 20 30 times. Now I'm going to multiply it 4 times when I go crosswise, right? For 80. Now 600 to 80 is in ratio 30 to 4, because this is what I multiplied by. Now I would multiply the 1, right? 130 to 1/4. Now, because these are in ratio, because the act of multiplying itself makes this ratio, I can take this understanding to algebra, and it makes very, very clear something students struggle with all over, which is factoring polynomials, understanding how polynomial expressions are created in the first place. This is the structure of it, and we'll start with trinomials to make it clear. So here you can see the structure of these binomials. We say binomial because bi means two, and nomial means name, roughly, from the Latin. So a binomial is just an algebraic term, or excuse me, an algebraic, term with two pieces, two names to the pieces, right? This is an x order of magnitude. This is a 2, or units. So if I use my vertically and crosswise pattern here, watch what happens. It's a lot like FOIL, first, outer, inner, last, but it's a little bit different visually, which makes a big difference to how easy it is to understand and operate. Here I have vertically would be x squared. Then I would have plus 3x plus 2x. And I apologize if my x's and pluses look the same there, plus 6. So now remember how we saw that ratio that was created by the multiplication. These are in ratio 1 to 3. Remember, when we have a variable by itself, there is an implied 1 as a coefficient, because there's just one of these. So these two are in ratio 1 to 3. And because we multiplied the 2 also by x and 3, you'll notice these 2 and 6 are in ratio 1 to 3. The ratio maintains. By the very act of multiplying, the structure is built in. So watch what that means. Let's call, when we combine the trinomial, we usually do a, b, and c. Because these two terms, 3x and 2x, are of the same order of magnitude, with the same variable, I can add them. I can add them together. So I say x squared plus 5x plus 6. Now this is the format you typically see a trinomial, and they say factor. How do I factor this? Well, this can be difficult to wrap our minds around without the area model or whatever else, unless we understand this proportion. Because let's call, when it was expanded like this, let's call this piece A. This first piece from the first multiplication we could call P. So I want A to be in relation to, or excuse me, in ratio to P, the same way let's call this one Q is in ratio to C, this last term, okay? I want A to be in ratio to P, the same way Q is to C. Now, A in ratio to P is like saying A over P. A fraction is another way I could say this. And because I know AP must equal QC, because this was multiplied here, that ratio has to be the case. I can treat this like a fraction in cross multiplication. So now I'm going to make a little more space on the board and make this bigger, and we can zoom in on exactly what I'm talking about to give you this aha moment. All right, so I've made it a little bigger and easier to see here. Now we have this A term in ratio to P, the same way Q is in relation to, this should be C. And now because I can write this like a fraction also, what that means is I can cross multiply, right? AC must be equal, A times C must be equal to PQ. Now, if A times C must be equal to PQ, then what I can say is, A, remember here, there's a little coefficient of 1. 1 times 6 must be equal to 3 times 2, which is true, right? 6 equals 6. And because I know that's the case, now what I'm looking for is this middle term when it was the trinomial. So if you were just dropped off in a math class and they say, okay, they give you this term in this form, factor this. I know that if I multiply A times C, that must equal the product of two pieces that add up to this. Two pieces that add up to this. And those two pieces must create an even ratio across. So now I can split this. Well, what are two pieces that add up to 5 and multiply to 6? Well, that must be 3 and 2. Are we in the right order here? Well, this must be 1. And so if this is 1 in ratio to 3, is 2 in ratio to 6 the same way? It is. And because this is the ratio in its most reduced form, we can't reduce it any more than 1 to 3. I know by definition that must be one of my factors, because remember, when we multiplied, the multiplication itself gave the ratio. So that ratio must be one of the factors. So one of my factors is x plus 3. And now to get my last bit, my other factor, all I have to do is divide this first term into this first term, and x squared divided by x is x, and this last term into this last term. 6 divided by 3 is 2. Because I multiply with vertically and crosswise, right? The vertical piece here must be defined this way, and the vertical piece on the end must be defined this way. And so this understanding, this simple pattern, we start with simple weenie numbers like 12 times 23. You don't even have to learn carrying, really. At least not in the beginning. You can start with small numbers and work your way up. But all this to say that it's not that you're stupid. It's definitely not that you're bad at math. Because remember, no one's anything all the time. It's that you bought into the idea that because you have a bad memory, Or, to your credit, a series of bad memories. Maybe you've had years of struggle and frustration with mathematics, and the groove is just so well worn that that's what you believe. I'm inviting you, though, not to confuse the stability of your memories, of your ideas, with the stability of the world. The world is very fluid, it's changing all the time. And I'm telling you, you are literally one thought, one pattern away from becoming so dominant at math that you build a reputation for being a math genius. Which leads me to tool number 3. And the third tool I want to leave you with is this, is that in math and science, I've noticed tutoring, the biggest and number one obstacle that people have to really performing at their best is to think they should already know the answer. I want you to get very, very comfortable with frustration and confusion. They're not bad things. I had anxiety problems when I came back from my deployment as a Marine, and I learned that neurologically, the pathways look identical when they're activated for excitement and fear. I learned that in my recovery process. So when you're excited, it looks exactly the same as when you're afraid. The only difference is how you're talking to yourself and how you define it. And so when you're confused and frustrated when you're learning, I want you to get happy about that. That's a sign that your brain is engaging with the material and making connections, and you are about to make a huge breakthrough. So if you enjoyed this video, if you're curious at all, if you would like to transform, to experience that transformation of going from confusion and frustration to clarity, confidence, and just a natural joy with mathematics, comment coach on this video. I'm taking students through a 13-week algebra and trig intensive, and I will give you everything I have, all the tools that allowed me to get my bachelor's in 6 months, and yada, 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 everything else I've talked about on this channel. Comment coach. If you need a coach, I can't wait to work with you. I absolutely love helping people open these doors in their mind and make a better life. Thank you for watching.